Okay, shall we start? Okay, so the second half we're going to talk about classification. Okay, okay. Before I start, everyone make sure you understand dummy variables. Any like confusion? Any? Just one more very simple explanation. Okay. Okay, let's say I have orange, banana, and apple. Okay. Now I'm going to change it to dummy. How would it look like? This is a list with 3 items. If I'm going to change it to dummy variables, how would it look like? We have orange, banana, apple, then we have 1, the rest is 0. Okay, that's what it means by dummy. Okay, so back to classification. Okay, just this graph, we saw it for many times. So this is how every model compare to the rest. Okay, so now we know gradient tree boosting is the best, but the disadvantage is you lose all the meaning for gradient tree boosting, just like PCA. Okay, so random forest is the second best. Okay, and in fact, random forest is, I think, is the most popular for data scientists because it's quite easy to explain and it's quite fast and it's quite strong as well. Okay, so today we're going to talk about several things. There's a model called KNN, K nearest neighbor. Okay, and we have something called decision tree, which we talked about. And we have random forest, logistic regression, and I'll briefly talk about support vector machines and naive Bayes. So these are all classification model. Okay, okay, what's classification? Do you guys remember? Okay, just differentiate the types. Okay, and if you think of it in the model terms, is differentiating the label. Okay, so if you go back to this shape, the y instead of a value, now it's like 1, 0. That's binary label. If not binary, you can put like orange and apple. You can do something like this. Okay. And okay, this time I'm gonna stick with just one dataset throughout the entire class. I'm gonna talk about the iris dataset. Okay, it's the I'm sure you guys have seen it. So iris is a preloaded dataset in library, and it only have 4 columns, which is like the length, the width of the flower, and how tall it is. Okay, and then we have different target, and the target is okay. We have 3 target, 0, 1, and 2. Okay, these are the type of the flowers, and this is the ground truth of the flowers. Okay. Okay, again, you can see this shape is exactly the shape I wrote. So we have the X, which is the first 4 columns, and the Y, which is the target. Okay. The more you work on it, the more you realize everything is just these 2 formats, X and Y. Okay. Okay, the first model I'm going to talk about is called KNN. It's the K nearest neighbor. Okay, and this is a supervised machine learning. Okay, the logic is super easy. Okay, So we have a lot of labeled data. Let's say you have x1, x2, or maybe you can do a PCA and do PCA1, PCA2. Alright? So now I have an unknown data right there, the gray one, and I have some labeled data with these three groups. Okay? What I need to do is I have to count the closest k neighbor. Okay, so let's say you just count, okay, this one is the closest, and I'm gonna take the second closest, and I'm gonna take the third closest. Okay. Then you look at all the neighbors you chose and see what are the majority. Okay, so in this case, the majority is this color. So now I'm gonna classify this as this color. Okay. So basically, you sit in your seat and just count your closest three neighbor, and then see what the majority are. Okay. And okay, just find the closest neighbor and fold on a label. Okay. And alright, let's say for this case we have a lot of fruits and we have the sourness and the sweetness as a spectrum. Okay. And now you can count your closest neighbor to see which group you belongs to. Okay. And okay, it's just quite simple. And the way they count the distance is just cosine, I think it's cosine similarity. Just the distance, you square it, and then you find this, you find the distance in here. Just high school mathematics.
So for the k nearest neighbors, the distance doesn't matter which class gets the most votes, and we'll categorize into that.
Sorry, I don't get what you mean.
For example, in your example, like the yellow.
Yes.
The yellow class gets 2 votes, but at the same time they are the nearest.
Okay, yeah, the distance doesn't matter. It only care about the closest, after you count the closest 3, what are the majority? That's the only thing.
The two, like, they are the farthest in the
Yeah, the ranking doesn't matter as well. Let's say you do like 100 neighbors, and then the majority is very far away, but yeah, you still count the majority. Okay, so there's one thing special with k nearest neighbor, is the k. So what if I choose even number for k? Then there's a chance for the chance that I can't get the majority. Okay, if I have chosen 4 nearest neighbor, and 2 of them are girl, 2 of them are boys, okay, then I can't really decide and have the majority vote. So for k and n, you always have to select odds number. Okay. And then okay, just a quick example. You load your iris dataset. You have your x and y. Okay, that's your y, and that's your x. Okay, your x is something like that. Okay, the way to do KNN is just define the model this way. Okay, when you instantiate your model, you have to set your number of neighbors. Okay, in this case, you set 3. Okay, and then you just fit x and y, and then now you're done. You can start to do predictions. Okay, and if you want to visualize how the KNN looks like, just scroll down a bit. Okay, this shows the area that every color belongs to. So one good thing with KNN is if you use another classification model, it usually draw the boundary like this. Okay. So in this case, this boundary is quite easy to draw. It's a pretty straight line. But let's say for this case, this is pretty hard to draw a straight line to extract. So KNN is good for cases like this. Okay. But what KNN is bad with is if you have a multi-dimensional data. So let's say you have 200 columns. Okay. If you need to compute the distance between 200 dimensions, it's going to be very slow. And your model size will be super big. Okay, so KNN is good when you have very little columns. Okay.
So it's not suitable to handle a large amount of data.
It's good for handling, like the number of rows doesn't really matter, but the number of columns matter. Because let's say if it's two-dimensional, the way you calculate the distance is just calculate this line. Okay. Let's say if you're three-dimensionals, you have to draw an axis right there, and the way to compute this distance will be more complex. Okay. Let's say if you have four axes, you have to, I don't know how to plot it, you have to do it by time, and if you have more and more and more, the complexity just adds up, and so your model will be very big. Okay. Okay. Okay, so after you created your model, you can use your model to do predictions. And how to do predictions is you just do dot predict and put your features. Okay, because your features is x, and this will be your predicted value. So let's say now you have a new flowers, and the dimension is like this, 2 and 3. Oh, sorry. Dot predict. Okay, doesn't work this way. I think you have to do this. Okay. Okay. After you shape your feature in the way that your x is, it's gonna give out predictions. Okay. So given this two dimension, the KNN we're gonna predict the class to be 0. Okay. And that's a way to tell how good your prediction is. So if you go back to our very first the model workflow, you have to understand the evaluation matrix. Okay, in classification, the evaluation matrix is how many times you guess the right answer given your unknown data. Okay. Okay, so to compare how many times you get the right answer, you do something called the classification report. Okay, and you have something called precision and recall. Do anyone heard of the terms precision and recall? No? Okay, so I'm going to explain it in 10 minutes. But precision, it's basically how many correct answers you got. So precision is your true positive over all positive. Okay, so let's say you have 100 orange and you predict 90 out of the 100 orange. You have a precision of 0.9. So you get it 90% of the time. Okay. And recall it's something else, but I'm gonna explain later on. Okay, so in this classification report, you have the row as 0, 1, and 2. Okay, this is your class, and you have precision. And 1 means you get all the 0 class correct, so it's 100%. And on your second class, you do not so well, it's just 82%. And for your third class, it's just 0.75. Okay, but you got an overall precision of 0.86. Okay, that's how accurate your model behaves. And then you can easily do a cross-validation, which is just fold it for 5 times, and it just give out your average prediction. Okay. So any question for now? Okay, if no, then we can play around with KNN. So your task is to try to use all features to create a KNN model. Do you want to have a try? Yeah, actually, I did the answer for you. I forgot. But okay, please have a read for like 2-3 minutes. And then okay, I'm gonna talk about it. So again, for every model, we have to figure out what's the x and what's the y. Okay, so in this case, what's our x? If we want to use every single axis, our x is our df. Okay, we want to use all of them, and our y it's our label. Okay. So to train a model, you have to instantiate an empty model, which is this. Okay. Just create an empty model by specifying the number of neighbors, and then you do knn.fit, and then just fit your features with your target. Okay, and then after you run this, you just train a model, and you put it into your classification report and see how well it gets classified. If you want to be proper, you can do a cross-validation score as well, which is this cross-validation. Okay, now it looks a bit better than the previous one. Okay, any questions for here? Clear? Or okay, so if I repeat more and more, you will just realize all machine learning model is just shape the data to that way, and just apply the model and see how well it fits. Okay. Okay, I'm gonna talk about precision and recall now. Okay, so for precision and recall, you can think of it a graph like this. So these two rectangles is the true positive and the true negative. Okay, these are the ground truth. Okay, and the ground truth is the color of the dots. Okay, this you have black color and you have white color. Okay. When you apply a model, you basically choose from this set and say, okay, now these are the correct ones. And now I make a circle like this. Okay, I made some error. These are the true positive, which means I select the right answer from the positive, okay, from the true ground truth. And we have something called false positive, which means the model say it's correct, but in fact it's incorrect. Okay. So we have 4 things. For precision, it's just this half of the circle over all my predictions. Okay, so given all my predictions, how many of them are correct? And recall means given all the correct answer, how many I get it right? Okay. So, okay. Precision. Okay, it's all predated positive. Our recall is the true positive over all the ground truth positive. Okay, so there are different things. Okay, I forgot what it's called. The denominator is different. Okay, so this one essentially means how accurate is your prediction, and that means given your original data, how accurate it is. Okay. So one is just compared to the rest of your predictions, and one is to compare with the original ground truth.
I understand precision.
Yeah.
The usage of precision, but how one use
Recall.
How was the result?
Okay, so let's say I have a farm. I have a farm. And they're all orange. Okay, some orange are good, and some orange is rotten. Okay, so now I build a model. I say these are the good ones. Okay, and we have like rotten orange and good orange, and okay, so out of my 5 predictions, 3 out of 5 is correct. Okay, so my precision is 0.6. But out of 1, 2, 3, 4, 5, 6, 7, 3 out of 7 is my recall. And I don't know how just do it. So we're talking about different things. This one is how good of my prediction set is. So next time I do a prediction, I would say there are 0.6 chance that I'm correct. But even this, it means out of all the ground truth, 0.5 like 0.5 times, I can get everything correct.
Which means if you translate to your example, because it means among all the orange font,
Yeah.
you can select a lot. I'm just trying to understand how does that work in the case.
It means out of, okay, how should I put it? It means out of all the good orange, probably I can only predict half of them as good orange.
Out of all the good orange, only half of them are good orange.
I can only predict it. So my model only can make this precision. Let me think of the good explanation of recall. Recall in simple words. Like, to be honest, for recall, sometimes I find it hard to understand myself as well.
Okay. But do you ever use it?
It's how you evaluate the model. So let's say if my goal is just to make correct predictions, I don't care about the overall coverage of my predictions. Let's say if I use this model to select orange, let's say I have a more extreme case. I do it this way. So if I use my model to predict a good orange, every orange I give you is perfect. Okay, but I don't cover all the good orange. So maybe some good orange in California is not in my model, but all the good orange in Brazil is covered by my model. So my prediction is good, but it's not covering everything. Okay, so does that make sense to you?
Not.
Okay, maybe I'll come back to you next time. I need to think of a good example to talk about. Okay, and we have something called F1 score, which is just the simple average between the two. Okay, recall and precision. Okay, so if we build a data frame like this, okay, these are the predictions and these are the ground truth. Okay, if I just select some sample out of it, like usually they're correct. Let's see. Okay, my predictions are very good. Can't find any wrong one. Okay, but some of them are incorrect. Okay. The way to calculate recall is just a true positive over true positive plus false negative, and if you put it this way, okay, basically what this does is select all the true positive for label 2 and then see how many of them are predicted as a 2. Okay. If I just count all the prediction, okay, 47 out of 50 are correct. Okay, so my precision is, my recall is 0.94. Okay, because I'm comparing with the ground truth. Okay, but if I'm comparing with my predictions, you are just dividing by different things. So I'm just selecting all my predicted 1 and see the proportion of false positive. Okay. So if you compare the two formula, one is find the truth first and see how my prediction does, and this one is find all my prediction and see how many of them are true. Okay. I know it's confusing, I find it confusing as well.
How the system define what you show is true is genuinely true or not?
Okay, you have your ground truth. Okay, that's your true positive. That's your true positive and true negative. And you can do a prediction. So this is your predicted. This is your prediction. And if you do it like this, then this is false negative. Okay, this is true negative, true positive.
So is it with the same similar mechanism as the cross validation?
Not really. Cross validation is you train on a subset and test on the remaining sets. But for this, you are evaluating your performance. So that's how accurate your prediction is. So if you predict 90 out of 100 orange, then you have a precision of 90. And your model is correct 90% of the time. That's how you interpret it. Okay. Okay, I guess I'll come back with this precision recall. But for now, just think of it as a measure of how accurate your model is. Okay, so we talked about KNN. We're going to talk about decision tree. Okay. Okay, so decision tree, you can think of it as a lot of split. Okay, and the tree tries to split in a way that it gains most information by splitting. So let's say you have a data set like this. It's longer than that. And you have a lot of features. And you're just finding a split in one of the features that best differentiate the ground truth. Okay. So let's say this is color. And this, maybe not color. Okay, this is a better example. Oops. Okay, so we have Ferrari and we have Toyota. Okay, and I have to find a split that best differentiate Ferrari and Toyota. So I have price in this column. Okay, and I see Ferrari usually sell for like 1 million, and Toyota sells for 200K, and this Ferrari sells for like 2 millions, and this Toyota sells for it's an expensive Toyota, 700K. So I'm gonna find split in the price that best differentiate the two. So in this case, probably I'll set the differentiation at 800K. So if the boundary is 800K, then I can say this is Ferrari, and because this is 2 million, it gets the Ferrari as well. Okay. But then what if there's a very cheap Ferrari and a very expensive Toyota? Then I can't get the split, right? So I'm gonna go for another features, say color, and I have like red and white color. Okay, then if it's red, then it's more likely to be a Ferrari. Okay, then I do another split. So that's exactly what the decision tree looks like. It's gonna keep on looking for your split. Say in this case, it's gonna be price bigger than 800K, and then you have yes, Ferrari, or no, it's a Toyota. Okay. But then, how the tree is created? How can the tree find the optimal cutoff? basically there are good cuts and bad cuts. Okay, if I do the cutoff in that case at 300k, it's gonna give me an error for Toyota. So we have to quantify what's a good cutoff and what's a bad cutoff. And we have a score called the Gini score. Basically, it just counts how pure is the data after you make the cut. And so if you cut it this way, you're not gaining any informations. Okay, but if you cut it this way, you at least made one side pure and the other side with like a few errors. So the Gini score for this case is better than this case. Okay. So let's say back to the Ferrari example. What the computer does, it just keep on trying a different cutoff until it reaches a point that it perfectly cuts one of the sides. Okay. If you visualize the decision tree in the iris example, basically it just keep on finding the cutoff. So you can see every line is either a straight line this way or straight line that way. So for every variable, it tries different cuts. Okay, and it just keep on cutting until it filters everything. And okay, if you try to visualize every single step in decision tree, you can do like first cutoff by the pedal width with this cutoff, yes or no, and this is all the truth. Okay, now you created a cutoff with all the true class 1, but some of them are remaining unknown, and you keep on splitting it until every single class is pure. So you have 47 class 1, 1 class 3, 3 class 3, and then 2 class 2. Okay, just keep on finding the cutoff. But there are two things to consider for decision tree. One is how deep you want to go. Okay, because if you keep going, you can always find the perfect model. Because you can have a split with just one item per group. Okay, so you have to control the depth. And secondly, you have to control, I think you have to control the minimum number of items in every group. So you don't want a case with just one item per group. Okay. And another important point is the same variable can be cut more than one time. Okay. So if you do a cutoff in price, and then you went to color, but the data is still impure, you can go back to price and do another cut. Okay. So after you created all the rules, now you have a new Ferrari coming in, which is not in the datasets. You just put the Ferrari and follow every steps and see which group it belongs to. Okay, if it's green, then it's group 2. If it's a different color, then it's belong to a different group. Okay. That's basically how decision tree works in the computer. And to put it into a group, to model, again, it's quite simple. Again, you just load the datasets, split it to X and Y, instantiate decision tree classifier, and just put your model.fit into your X and Y. And again, you can, Okay, you can check your classification report. You should be expecting perfect score for your decision tree. Okay, if you like use your training data to evaluate. Has to be perfect. Okay. Yeah, and the parameter is just the depth and the number of item. Okay. In this case, you're just doing a very shallow tree, but the performance is still not too bad. So this is pure. This is 1 error, and this is 5 error. Okay. So usually we should aim for a very simple model for a decision tree. Shall we keep on with the class on Thursday, or do you wanna stay till 10? Okay, let's do it next Thursday. Okay. So any question with the class? So thank you guys.
Thank you.